Welcome everyone. In this video I'm going to continue the CH32 tutorial series, and in this video I'm going to show you how to use an SD card with this microcontroller. So in my previous few videos I have already shown how to use the SPI with an external module which was an accelerometer, and then I also showed another module which was a thermometer, and then I showed how to read data and how to print the data from the thermometer in Celsius degrees. So in this video I'm going to combine those things with the third thing, which will be the handling of an SD card. So as you can see here, I have already prepared everything. So I have my usual development board right there, and then I have the wires set up for the SD card reader right here. And those are just simply the SPI wires, but one exception here is this brown wire, this one here, which is leading the 5 volt from the debug module to this red wire, because the module itself, which is this one, the SD card module, works with 5 volts, so it will need a 5 volt input. You can see the onboard voltage regulator here, and that is then converting down the 5 volt input to 3.3 volt, which is later needed for the rest of the components on the module. And then finally we have the thermometer module here, which is just the previously introduced DS18B20 digital thermometer. And as I mentioned, we have the debug module, so that will provide me the possibility for programming the microcontroller and also to communicate with it via USART. So the module for the SD card is sitting here, but I have to plug it into the board. And the setup will look like this. So I will insert the SD card when it is time, but then so far you can see that we have the thermometer module, and then we have the SD card module and the microcontroller setup for this demonstration. And when it comes to the FatFs module, then I'm using the resources I found on this website. So we can find a very nice library which needs a little bit adjustment to make it work with the CH32 microcontrollers, but otherwise we can read all the documentation here, and then we can download a bunch of resources. So we have sample programs, and we have all the necessary information that we can use here to develop our program for the CH32 microcontrollers. And in this video my demonstration will be a little bit different than the others, because I won't go through the code line by line, because we have a bunch of files in the library that we have from the FatFs module, and it would take days to explain everything, and therefore I will just show you how to set things up and how to make things work. And at the end I share the whole project file on my GitHub page. Then you can just copy the whole project file into your folder and then open it, and it will hopefully work with your microcontroller as well. So the module that we can download from the FatFs website has these files that you can see in the file explorer, and they have different purposes. So the disk.io.c and .h are the low-level disk.io module files, and then we have the ff.c and .h, which are the generic file system module files, and then we have a very important file which is the ffconf.h, and I will explain this in a bit more detail. This is the configuration file of the FatFs module. Then we have the ffsystems.c, which is a collection of OS-dependent functions for the FatFs module. And then we have the ffunicode.c, which is used for handling the Unicode functions for the FatFs module. And actually this is not all that we need to operate this library. So we will create two other type of files, one to handle the SPI communication and the other to handle the communication with the SD card. And as I said, I share all these files on my GitHub page. So go to my website and then go to my GitHub page following the link from my website, and then you will get access to the SD and SPI related files. So in my case, what I simply did is that I created a folder in the user folder of my CH32 project folder. So as you can see, we have the main.c here, but then there is a folder here called SD card. And after opening that folder, we can see that the first few files are from the FatFs module or library. And then we have the SD and SPI files, which are developed by us by combining my stuff from the SPI tutorial that I released recently and some knowledge that I found on the internet on forums and different manuals. So then let's look at the source code together and let me show you what I wrote here. So first of all, I created a folder called SD card under the user folder where I store my project files, and I put all the relevant resources there. So all the FatFs files are there, plus the SD and SPI related files can be also found there. So some changes that I did can be found under the sd.c file, and I implemented the SD card insertion detection in a bit more detailed way. So how it works is that certain breakout boards, for example Adafruit's breakout board, have the CD pin available, and then we can detect the state of that pin, and based on what is the state of the pin, we can decide whether the user inserted or not an SD card into the socket. And then there are also two predefined baud rate prescalers, as you can see it here, and they are needed because in the beginning we have to set up the SD card in a slow speed, and when the initialization is completed, then we can change to a higher speed, so a lower prescaler value, and that we will utilize in this code. And then the SPI.c can be already familiar to you, because this function, which I highlight right here, was already implemented in my previous video where I focused on the SPI basics, and here I have basically exactly the same. So I assigned the chip select pin to PC4, and then I use the default SPI pins for the rest of the pins, which are the SCLK, MOSI and MISO pins. And then later on we have two more functions. One is to change the baud rate dynamically, and then the other is to transfer byte between the SD card module and the microcontroller. And the little addition here is that both the send and the receive parts of this transfer function wait for a while. So if there is nothing in the buffer in the first try, then there will be several retries, and if those fail, then the function returns with 0, but otherwise it proceeds, and then it sends the data and receives and returns the data. So then we are back to the main.c, and then we can focus on this part of the code a bit more. So we have these libraries here, or header files, and then you can see that a few files which are related to the FatFs library are defined with a bit funny path here, because I introduced an extra folder into the user folder, and this is how I can reach now the header files. And then I have this global define of debug. So if this debug is set to 1, then we have a macro here that we can call, and then all the printf function, which looks like this, will be used. And if I change the debug to 0, then the printf functions will not be used, so I will not be able to print on the serial terminal. And why I did this is because I only want to use the serial terminal and the serial communication between the microcontroller and the computer when I'm developing the code, so when I'm debugging it and so on. And when I'm finished with the code, first of all, I might use the microcontroller in standalone mode, so it is not connected to my computer and I don't need the serial terminal. But also, this specific code uses a lot of flash memory, so then I have to be very careful and very frugal with the space available. So therefore, I want to disable all the USART related stuff so I can save more space. And then I define the SD card detect port and pin here, and you can see that the definition coincides with the chip select pin. And here I have to heavily emphasize that I'm cheating here. My module that I have doesn't have a chip detect pin. So I just simply assign it to the same pin as the chip select in the beginning, and then I will do some detection on that pin. But this will be irrelevant, and if you have a module that has the chip detect pin, then you have to assign it to that. And then we have a bunch of variables. Some of them are related to the file operations, and some of them are related to the temperature measurement, because as I mentioned in this demo, I will use my already developed code, which I developed for the DS18B20 digital thermometer. So that will provide us the data that we will log on the SD card. So I will need some buffers and some other variables for that part of the code. And you can see that we also have a welcome message, and this will be inside the text file which we are writing on the SD card. So down here we have the regular default USART function, and I explained this in one of my videos, so I'm not going to do that. And then if we go further down, we can see that all these functions are related to the temperature sensor, so I'm not going to explain them either. But there is one function that I'm going to explain, and that is the conversion function that converts the raw data from the thermometer to a floating point number. And these three lines that I'm highlighting right now, they are exactly the same that they were in the previous video. But then you can see that now the function returns with an integer, which is created by this snprintf function. And what we do here is that, first of all, the return value of the snprintf function is the length of the buffer that we are printing with this function. And we can see that actually what happens here is that we take the basically float now, so the 2 decimals with a dot separator here, and that we put in the buffer. And then that buffer will be the buffer that we pass to this function here in the parameters. And we also will have the buffer length, which is also mentioned here in the parameters. And therefore, the conversion value, which is now expressed as a, let's say, string of characters, will end up in this character buffer. So this is one difference as compared to the previous implementation of this function. Then the more exciting part happens in the main. So in the so-called setup part, I put a condition here as well. So if I don't need the USART, I will not even call these functions, so they won't be compiled, and the code will take up much less space. Actually, I save like 2 kilobytes of flash space, so it's very good. And then before doing anything with the SPI and related stuff, I have to run this set chip detect function, and then I pass the port and the pin, which is port C, and you can see that that is defined as GPIOC, and this will be pin number 4. So I pass this to the chip detect, and then that will just assign the pins as it's needed. And then I put this comment here. So again, I'm kind of cheating here because I define the detect port and pin to be the exact same as the chip select pin. And later on this will be written over by the SPI initialization. So it will not matter, but in the beginning I will use this as an input. And then we print 2 lines on the serial port, and then we start to count down, so we can give the user a little time to potentially insert the SD card if it's not there yet. So you will see it when I'm showing it to you through the serial terminal. We print a dot every second for 10 seconds. So this point or dot will be shown as a progress bar. And then what I do here is that I call this SD_detect function with the corresponding pins, and then the return value of that will be the status of the SD card detection. And if it's present, then the function should return 1, and if it's not present, then it should return 0. And then I print this value just to see what is happening. And then based on those numbers, I can do something. So if the card is not detected, so if it's not 1 in this case, then I tell the user that the card is not detected, and then I get the code to stall here. So it will stop here because there is an infinite loop here. So the user can insert the SD card and reset the microcontroller to start over. Otherwise, if we have a card, we can initialize the SD card, and then we can see what happens. So if the initialize returns with a 1, that's actually an unsuccessful operation. So we print SD card error. But if it was successful, then we print the corresponding message to the serial terminal, and then we will determine the size of the inserted SD card. And finally, we switch to high-speed operation, because in the beginning, when we start up the SD card, we started with a much lower speed. We were using 256 as the prescaler value for the SPI clock speed, but in this case, we will use 4 as the prescaler. And then we have this fmount function. You can see that the mounting is not included in any of these if-else blocks, but if the card is not detected, we anyway get stuck here. So the only way for the code to reach this part is to go through this branch where we actually have a detection, so we can initialize the SD card. And then, based on what is happening, we go through these if-else blocks, and then finally we start a reading test. So what we do is that we have this readtest.txt file on the SD card, which I'm not going to show you right now because it's a bit funny what I'm printing there. And then, yeah, we open this file, and in this while loop down here, we start to read it. And we read each line of the file, and we print it in the serial terminal. And I set up this while loop in a way that every 1 second we print a new line. And there are 2 things to mention here, is that currently the SD card library is set up in a way in the ffconf.h file that the maximum length of the file name can only be 8 characters. So if your file name is more than 8 characters, then actually this part will fail and we will not be able to read the file. And this is to save some space, because if the long file names are enabled in the library, then it will take up much more space. So we are saving space, therefore we can use only maximum 8 characters as the length of the file name. And then one more length related parameter is the line. So you can see that the line variable is defined as a character array with 64 items. And actually that is just 63 because we have a null terminating character. But what I'm trying to say here is that if a line has more than, in this case, 63 characters, then actually the printing of a single line will be split up into multiple printing, depending on how many times 63 characters we have in a line. So either you decrease the number of text in your text file that you want to print, or increase the size of this buffer, but in that case you will consume more memory. So you have to do a compromise here. After we read the file, we close it, we wait 5 seconds, and then we proceed to the write test. And again, we have a funny file name here, because I cannot put the final T here, because then the file name would be 9 characters long. So that is not good. So I just make it 8 characters long. And you can see that this switch fa_create_always, that says that we create a new file. So even if this file with this name exists on the SD card, we will rewrite it and we will basically erase it. And then we open this file also not only for overwriting, but we also write in it. And that's how we do it in this, let's say, declaration or definition. And if everything goes well, then what we do first is that we write the header in it, in this line. So if you remember, we created this MSG, which is our welcome message. And you can see now on the highlighted text that that is the name of the tutorial, basically. So this will be in the first line of our file. And then If everything went well, we close the file and then we proceed to the main loop of the code, which is the while. So I created this counter here, and why I did it is because I don't want to keep writing into the file or on the SD card. I want to print a few times, and then I want to be able to just suddenly remove the SD card and check the results on my computer. So that's what we exactly do here, is that we first indicate the user that there is an update happening. So we print on the serial terminal, and then we open the same file that we created previously. And you can see that we are just opening it, but we are opening it for a write operation. And if it goes well, then first what we do is that we run this f_l seek function, and we determine where is the end of the file, because we want to write to the end of the file. And if the end was found on this file, we skip this, because you can see the condition is that if the fr_OK was not the result, then we do this thing. But we jump over it because let's say it was successful, and then we do a temperature measurement. So first we inquire the raw data, pass it to this variable here, and then we convert the raw data into a floating point number. And that's here what we exactly see is that we take this function and then we pass this raw variable to it, and then the output will be stored in the line buffer, and then the length will be the size of this line buffer. And then also the length will be passed to this length variable, because that's the return value of the print float temp function. So then we take the f_write and we open our file, we pass the line buffer to it and the length of it, and then we write into the file. And if that went well, the code ends up here where we can close the file, we can increase the counter and wait 1 second. So this while loop here, which is now visible on the display, this will run 10 times, and every second it will write a temperature value, a new temperature value, into the file on the SD card. So now what I'm going to do is that I will bring up the serial terminal after I reset the microcontroller, and then we will go through the events that will show up on the serial terminal. So here we can see our growing progress bar, and we have to wait a bit. And then we can see that the return value here is 0, and that means that the SD card is not detected. And if we go back to the code, then we can see why is that happening. So we ended up in this part of the code, and what is happening is that we returned with 0, which is the not present status. And this is again because I'm cheating here and I'm not using the chip detect pin, but I'm just reading the chip select pin, which can be whatever status depending on where we are with the code. So I'm going to cheat here again, and I'm going to flip the status of this function. So when it returns 0, actually it will write 1 in the card detect variable and vice versa. So then in the next compilation, my code will hopefully end up in the card detected branch, and then we can proceed with the rest of the demonstration. So we are waiting for the progress bar again. And now we can see some more promising messages. And now we can see the update message, which means that we are writing new temperature values to the SD card. And now I'm touching also the temperature sensor, so we can see fluctuating data when we are checking the contents of the SD card. But to check what happened here, we have to go back to the beginning. So I restarted the microcontroller, we got the welcome message and the instruction that we have to insert the SD card, and then we got our progress bar. And after that, so after 10 seconds of waiting, we returned with the card equals 1, which means in this simulated scenario that an SD card was detected. So the code proceeded, and then it initialized the SD card successfully, because then it found the size of the SD card, which is an 8 GB SD card. So this is corresponding to that. And then it also successfully mounted the file system, so that is good. And then this is the reason why I did not show you the content that I'm going to read from the SD card, is because I put some nice bagging message here. So you can see what I printed here. So this is indeed the 12th part of my tutorial series. So we are progressing very nicely. And then I just wrote that, yeah, you should also check out the rest of the playlist, because there are some interesting projects. And if you like this kind of content, then yeah, of course, you should consider becoming a channel member. So please do that if you can. And then once I printed these messages to prove that I can read from the SD card, then I started writing. And then this first message came from the result of printing the header on the file, because now first we printed that MSG variable and its contents, and then we got this nice number here, and we proceeded 10 times and noted down the temperature values from the temperature sensor. So now I can in fact insert the SD card into the SD card reader of my computer and see what is written on it. So here comes the file browser, and if I open this file, we can see its contents, and it's exactly the same stuff that I printed on the terminal. So if I go here, you can see that they match. But what is more interesting is what we wrote on the file. And then you can see that we got back our nice header that we created. And then, as I said, I touched the chip. So you can see that there is a slight increase in the temperature. So we have the room temperature, nice and toasty, 23.6 degrees, which I think it's not really true. And then it started to go up as I held my hand on the surface of the chip. So both file writing operation and file reading operations work as we expected. So as a summary, we learned how to work with the CH32 microcontroller and the FatFs library to make it possible to read and write information to and from an SD card. So now you could see that I could read what I created as a TXT file, and I could also write a new TXT file. And this is very useful if you want to have, for example, a temperature logger or whatever data logger placed somewhere remotely. With this device, it is possible. And as you can see it on the display, this is the article which I wrote in this topic on my website. So I encourage you to visit my website. Link is in the description, because I highlighted and explained the more important parts of this topic in the article that I wrote. So please visit my website. Plus there is a link at the end of the article which leads you to my GitHub page, where I shared the whole project file for this specific project. So you can just copy paste it into your Moonriver Studio folder, and then you can develop it according to your own requirements. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.